Greetings, welcome. So in the last video, we got the machine spinning. I can't remember where it left off, but the whole two-sided rotor thing didn't work. So we've gone back from the Mark 1 to the Mark 0.5, which is just half the rotor. But I figured let's start gathering data on that. And I thought the first thing to take a look at might be, let's look at the air gap, Where is it? Here it is. I mean, that's an interesting question. I mean, do you want a big air gap? Do you want a tiny air gap? And, start out simple enough. I think it's going to be like 3 or 4 parts before it finally gets done. But I finally got started with that, and I'm starting to gather some good data there. And, I find it kind of interesting. So here's the first part. I'm just like getting everything set up, and then in the subsequent parts, you're gonna, wow. You're gonna see like what it does with different air gaps. So I don't know why I like this stuff, but I'm having fun. And if you want to come along, then here it is. So if you followed along on the last video, we got the thing spinning, which was nice. And now, let's have some fun with it and just like start gathering data. And this is actually someone commented on this, and I got to thinking about it, and I thought that is a good place to start. Let's look at the air gap and let's see what we can find out about that. Now, it kind of sounds simple to start with, but there's going to be an awful lot to this. So let's just kind of lay the background here, and then we'll see if we can, have some fun and gather some data. So the very first thing here is I've retreated from the Mark 1 all 3D printed machine to the Mark, those things are strong, the Mark 0.5. And so instead of this being on top there and that all being one rotor, I'm just going with half the rotor. And the reason is that I'm having trouble getting the bearings to match exactly, and it creates a lot of friction. And this thing spins much nicer now, and there's a lot less wobble and friction, and so it really doesn't mind spinning up with a very small amount of power. But having retreated like that, this is really similar to what I was just doing a few months back. But, at least now maybe I'll try and be a little more methodical. Whereas a few months back, the magnets were facing out this way and the coil was here. Now we have the magnets up here and the coil will be there. I'm going to run with air cores on all this just because I don't want to worry about the iron attracting to the magnet. That's why I'm running an air core. Might do better with an iron core. But as I said, even really simple things like the air gap, it's very counterintuitive. Let me get those other magnets out of the way so that there's not a mishap. But I'll just tell you what I'm seeing, and it makes zero sense to me. And that is when you have a big air gap, the thing spins fast, okay? So you say, all right, well now I'm going to bring the coil in closer. It's going to spin faster because, the coil's closer to here. No, it spins slower. It spins slower, and it draws less amps. I got no idea. So that doesn't really make any sense to me. So what I'm going to do is to confirm that, and then there's just a whole slew of variables to think about here. Now the first one is when you're triggering your coil. And when I see that is, they talk about having the trigger offset about 22 degrees. And I've never looked at it when it's top dead center. Now, that's also something that tremendously affects your amp draw and your rotational speed and things like that, is where you're triggering it. So is it happening only at that 22 degree point, or is it also happening when you're right near top dead center? Then what's happening with the radiant spike. And then the last question, I think this is one that I'm really interested in. What's happening, what's happening to the torque as you bring this thing in? So it slows down, but I think the torque has to be higher. I mean, you can go out to, just an absurd example and like put this coil on the ceiling, and this thing's not going to spin. And so as you're bringing it closer, the closer you get, I would think the torque would be increasing more and more. But I don't know why the amp draw goes down and the thing slows down. And again, I mean, eventually, you could have an absurd thing where the coil is so far out. But with a really big air gap, it still spins fast, and then it starts to slow down as you get closer. So how do we look at this? And there's one thing that I want to try to get straight when I do this. I haven't done it yet, so I don't know how it's going to work, but I think, this makes sense. You're going to be changing the distance between this and your coil, and so you don't want your sensor also changing distance as you change that distance. In other words, you want the sensor, I want the sensor now on the ground, just keep this thing right in the same place and move this plate up and down here to change the air gap. Because otherwise, if your sensor was on here as you're moving this up and down, then you would be changing the duty cycle and the pulse width along with changing the air gap. And we want to keep the pulse width constant and just change the air gap. So just leave the sensor down here, and then we're going to move this shelf up and down. So how are we going to do that? So you see, you put the shelf there, and that's a pretty small air gap. I mean, I could make it a little bit smaller, but that's relatively small. I'd say like a 1/4 inch, maybe a little bit more. You try and get it down to like an 1/8 or a 16th, but that's a fairly small air gap. Then you have your coil sitting there. Now, I'm going to use just this high-tech approach here. We'll use 2 different kinds of tape. Okay, so this is just an absurd air gap, and this is actually, like it on the ceiling. I mean, we can see it's putting current out to the coil, and it's just too far away to really keep spinning. So let's just make instead of an absurd, let's just make a silly large air gap with this tape. So now we just have a sort of a silly big air gap, and we're only running at 4 volts too. That's the other thing here. But if we do that, are you going to do anything? It's not doing anything. Do something. Okay, once I had the sensor there, now it's spinning up. And what'll be interesting is that it's going to spin up to a pretty good speed. So you can see, all right, the light came on. I like it. Even with that air gap, it's spinning pretty fast, and we're drawing about 125 milliamps with 4 volts. So that's kind of neat. Now, if I move this around, there are places it's not as dramatic with the air gap this big. Give me a second. It's not as dramatic. The difference between, well, that's just disconnected. Okay, what I'm trying to do now is just make sure that I have 2 consistent spots where the sensor is. So for the first one, and I'm guessing that, I'm just eyeballing it, but I'd say maybe that's close to 22 degrees offset. And the corner is bumping into there, and this edge is lined up with about the third line there. So you know when you do that, you're in about the same place. And that's what we're drawing there. Now what if we want to go top dead center? Now this gets real high tech. Kaboom. Put some balsa wood there as a consistent spacer. And now do you want it lined up third again? Yeah, I think so. It's about lined up in the same place. You're not quite top dead center, but you're a lot closer to top dead center now. You can see that's the amp draw. And we'll look at the speed, and we're going to look at the radiant, the inductive spike, top dead center, 22 degrees offset. And then the last part is going to be to put some resistance on it. So, you know, you could try and think about like mechanical resistance. It would be tough to make it consistent. You know, like if you had a sponge there or something like that, it'd be tough to make that consistent, you know, without an expensive setup. What do they call them? I don't know, I want to say like pawn brakes or something like that, but where you actually measure torque. So you could put in pickup coil. Now the problem is you can't put the pickup coil up top because the air gap's going to change, and that's going to change the resistance from the pickup coil. So what you could try and get away with, now this isn't how you normally capture anything off a pickup coil, because of course the magnets are facing that way, not this way. So you're only capturing the what would it be, radial flux, I guess. But I'm hoping this has got a lot of thin wire. So I'm kind of hoping if I put this through a bridge rectifier and then a low resistance, that it will slow this thing down. And then have this in the exact same place, so that when you connect the resistance, it's going to do the same thing each time. And then you can just measure the voltage too to see what's going on there. As we'll see here, you know, I think this air gap's so big that when we drop it a little bit, it's going to speed up more. But then you drop it more, it doesn't keep speeding up, it starts slowing down. But I think the torque will be higher closer in. It's like one of the big questions I have here. And then also just look at the inductive spike. So why don't we grab the inductive spike, set this up, then gather the data for this, and then we'll make one. We'll cut this length in half, and then we'll drop it all the way to the bottom. So three different air gaps, 2 different sensor places, like 5 different data points. So I don't know if people are having fun. I kind of have a ball with this stuff, but I mean, I have no clue what I'm doing. You know, let's just get that out, you know, in the open right away. But it doesn't behave the way I expect it to, and that's kind of neat. And I just want to see how it behaves. So let me do that. What I was saying. So if you want to capture the inductive spike caused by the changing magnetic field on the coil, what do? Well, you put here's a cap across the 2 ends of the coil, and then you put a backwards diode going from the positive to one of your legs of your cap. Now, you could use what's called a full wave bridge rectifier, 4 diodes, but because this is monopole, I don't see any reason why you would need to do that or why that would help. So you just use single diode rectification, and you remember that this is an inverting transformer. So even though this leg of the cap is going to here, which is the negative ground for your coil, that's a positive leg. It's putting out a positive, an inverted voltage into the cap. Now it's funny, stop reading. One of those alligator leads was bad. So we put that back on here. Now I fried the the amp meter on here, but it still works as a voltmeter. But it's funny because I was looking at this, it was actually on a different meter, and I'm like, I can't believe it's 0.83 volts. What am I doing wrong? And I spent like 2 minutes like, oh, it can't be, you know, this is 3 volts. It's got to at least be 5. That's 83 volts, not 0.83. That's 83.2 volts. So that's kind of neat. You know, you got 4 volts here, you got 83 coming out into there. Now this is a 2.2 UF cap, and the amperage is tiny. You know, the way this thing's set up right now, and there's a lot of reasons why it's inefficient. You know, I don't know a great deal on this, but I mean, I can make it a little better than, it's getting like 4 or 5% back. But what's kind of interesting is with a fairly high resistance load, we'll use like a 1K ohm. I don't have the amp meter hooked up right now. The amp meter doesn't change at all. If you go down to about 100K, it starts slowing down just a little bit, and this goes up just a little bit. You know, people who set this up where, you know, instead of going into a cap, it's charging batteries. One of the things that I've heard said, and I've kind of seen myself, is when the battery's dead, it does slow down a little bit. And then as the battery charges, this starts to speed up a little bit. And you can see that by going from like a 1K to 100 ohm resistance. And with the 100 ohm resistance, this will slow down. It does draw a little bit more amperage, not much, but a little bit. And so I would say that probably the resistance of a dead battery is, you know, closer to 100 ohms, and a charged battery is like 1,000 ohms or a bit more. So that's kind of neat. But we're getting 83 volts out there. And the last thing, if I can do it, and I don't know if this will work, but just, you know, to continue on with this. So what we'll do is I'll confirm that this is a 1K ohm, and we'll put that across here, and we'll see the voltage here plummet. So I put the 1K across the cap there. You see this voltage has dropped down to 2.0, 2.1, somewhere around there. But the amp draw is right where it was, just right under 150. So I don't think the amp draw changed at all. Now with 100 ohm, it might go up to like 155, 160 or something like that. But, you know, by Ohm's law, now you can figure out, you know, the voltage, you know, the resistance, you know, the amps. This is a tiny, tiny amount of milliwatts you're getting out as compared to what you're putting in. Like I said, it's like maybe 5% back. But because that didn't change, that's like a, you know, just a 5% boost there. And in later videos, we'll talk about trying to improve what you're getting out here and hopefully not have this change so much. There are some, there's one thing that works really well, and it's just crank up the voltage. But what we're concerned about now is air gap. So what's the last thing to do? The last thing is, can we put a way to have a resistive load on here that will be consistent each time? So let me see if I can come up with something for that. So this is far from ideal, but this is the only thing I can come up with. And I suppose I could put this on a box. It might be more effort than it's worth. So this thing is facing sideways against the magnets, which, you know, you hardly wouldn't expect to get anything. I'm getting, you know, 1.2 volts out, and then I have like a 100 ohm resistor there. If I connect that across the cap, give me a sec. You know, it drops to there, slowing down a tiny, tiny bit. Maybe I'll try a 10 ohm instead of a 100 ohm resistor. But that, for the moment, that's the best I can come up with. I just want like a consistent resistance that I can connect and disconnect. And it would be nice if it was pickup coil, even though this is the wrong way to set up a pickup coil. You can kind of hear it slowing down. I'm going to try it with a 10 ohm, but I'll show you one thing real quick. So I disconnected the resistor across this cap. You know, we're back there to 80 volts. Now, if I just put my finger on here, it's going to be real easy to slow down. So I don't know if I can just slow it a little bit, but we'll see. Well, you'll see the amp draw go up because the reactance of the coil, that it's a longer pulse. Well, it's hardly going up there much at all. But see how the thing's barely turning. We're still at 78 volts. And let me do that once more with the resistor back in place. Okay, it's going to take forever to spin back up because the air gap's so big, it just takes it a long time even just to get spin into a few hundred RPMs. But the point being that I'm pretty sure, you know, even if you like have the rotational speed, it doesn't have a big effect on the spike from what I can tell. And looking here, it doesn't have a big effect even on the amp draw, although that, you know, needs to be looked at both with top dead center and 22-degree offset. I'll tell you what, I got the test bed set up now. Rather than me doing, you know, like some 4-hour video or something, let's just stop this one right here. And in the next video, we'll have our answers in terms of how the amp draw behaves, how the rotational speed, because I haven't even measured the rotational speed behaves, how the radiant behaves, maybe if I can get any decent data, how it behaves in terms of resistance, how that behaves, which will answer the question about torque. And I think we're going to see some pretty odd things as we make this smaller and smaller. And again, one of the main questions I have, and I think, you know, this one is like, it's got to be, I think the torque's going to increase as this becomes closer to the magnets. But there's going to be a point here where it's spinning fastest, and then you keep going in closer, and it'll start spinning slower. At least that's what I've seen before. We'll see if it does it with this one. Okay, so that's it for this video. But it isn't even just amazing, the thing, off of 4 volts, the thing can spin with that big of an air gap. I find that pretty surprising. Pretty cool. So thanks for watching, and stay healthy, everyone. In the next video, I hope to have answers for how things change as we make this air gap smaller and smaller. Stay tuned. Bye-bye.